Hello, everyone. So we've been talking a bit about the second law of thermodynamics and the Carnot cycle and the fact that the Carnot cycle is the most efficient engine that runs between two heat reservoirs. Now, that's all very interesting. That's really non-intuitive. But there's something missing there. We really don't have a good intuitive understanding of what's going on with the second law of thermodynamics. And we're going to start to move in that direction today with this pre-lecture. So we've talked a lot about the Carnot cycle and the limits of its efficiency, but what we want to get to is a more intuitive understanding of the second law. And for that, we need this concept of entropy. And so I'm going to introduce the concept of entropy today. And it's going to take us quite a while to realize what entropy is, or to gain a kind of intuitive understanding of it. But for now, I'm just going to motivate one way of understanding it in terms of heat flow, and we will continue working with this in the coming lectures. Let's start with the Carnot cycle, and let's try to notice something curious here. So remember that the Carnot cycle has heat coming in along the isothermal step. So maybe if I'm going around this way, around the Carnot cycle, I have heat coming in. Let's put it like this. So Q in comes in during the isothermal expansion, and then Q out is exhausted in the isothermal compression step. And we've got our hot temperature here. Let's call this TH. And then we've got our cold temperature down here. This will be TC. So this here is the isothermal line of the cold temperature. And then this is the isothermal line of the hot temperature here, right? Last time we worked out the efficiency of the Carnot engine. So eta of the Carnot engine is 1 minus T cold over T hot. This is for a Carnot cycle. Now we also know that eta in general is this, right? 1 plus Q out over Q in. And I'm going to combine these in a certain way. So let's, what do I have here? I have 1 plus Q out over Q in. So for a Carnot engine, this will be equal to 1 minus T cold over T hot. And the ones cancel out. And let me write this a different way. So that'll be Q out over TC is equal to minus Q in over TH. Okay. And let me just write that one more way. So I'm going to put everything on the same side. Q out divided by TC plus Q in divided by TH is equal to 0 around the Carnot cycle. Okay. All right, so take a look at this. There's something interesting going on here. What does this term mean? This is the heat expelled from the gas divided by the temperature at which it is expelled. And this term here is the heat added to the gas divided by the temperature at which it's added. And when you add those up, you end up with 0. So you have this kind of interesting thing. I can write it even more formally. Sum over I, Qi over Ti is equal to 0 around the cycle. And this is the heat added in step I divided by the temperature at that step. So this is heat added in step, let's say I, and that's the temperature at which it's added. what does it mean to have something be equal to 0 when you go around a whole cycle? We know that if you start at this initial point here, and then you go around the cycle, and you end up back at the initial point, that the energy hasn't changed, because energy is a state variable, right? Here we have something else, which is this funny combination of heat divided by temperature. And when I add that up, I also have something which doesn't change around the whole cycle. So this is a hint that there's a new state variable hiding, which we didn't notice before. It's a hint at a new state variable. It doesn't change as I go around the cycle. So if I go around a cycle, I do something, go this way, come back. My initial point is equal to my final point. And if I do that, any state variable, because I end up back in the same state that I started at, the change in any state variable will be 0. And we're seeing that if we do this, the change in this is also 0. So that means that maybe this is a state variable. And in fact it is, and it's called entropy. Okay, so this is called entropy. The name comes from Greek, which is changing. And here's the definition. ds is equal to dq in a reversible process divided by t. And you can see that hopefully jives with what you're understanding from above here, right? The Carnot engine is a reversible process. So I'm breaking the cycle. So I'm breaking the cycle into a bunch of pieces, and in each piece I'm adding heat reversibly. That's what we did for the Carnot engine. Divide by the temperature at which the heat is added. Okay, what does this mean? This is an infinitesimal change in entropy. And how do I find that? I add a tiny amount of heat, infinitesimal amount of heat added, in a reversible process. And T is the temperature of the system when the heat is added. Okay. What are the units of S? Pretty clearly, the units of S are going to be the units of Q, which is energy, divided by the units of temperature. So that'll be joules per Kelvin. And just like with all the other state variables, we have specific entropy, which is the entropy per mole. So the small s is going to be equal to the big S divided by the number of moles. And the units of the specific entropy, small s, are going to be joules per mole times Kelvin. The expression that I wrote above there is the infinitesimal change in entropy. What if I am doing something which is not infinitesimal? So like what if you have a real process where you're adding a bunch of heat, not a tiny amount? So let's say I start with P here and V here, and maybe I've got some process starting some initial position and some final position here. Just initial state, final state, and I maybe go through some process, just write something abstract like this. How do I calculate the entropy change for that? Well, the idea is, like most things, if you know how to deal with it infinitesimally, You just have to break it into really small pieces and then add those up. So I'm just going to imagine a bunch of really tiny changes. And in each case, I'm adding a little bit of heat. And the temperature is what it is of the gas. And I just add all those tiny changes up. So a finite change is equal to just add up all the infinitesimal changes. And of course, adding up a bunch of really, really tiny things is the same thing as doing an integral, right? So the change in S, delta S, is going to be equal to the integral ds, obviously, from some initial state to some final state. And then I use the thing above, and I just substitute it in. dq divided by t. So there's our definition of entropy. We have the expression up at the top here for an infinitesimal change. And then if I've got a finite change, I just and add up all the infinitesimal changes. I've only motivated by looking at this, that this is a state variable, that entropy is a new state variable. But I'm going to try to convince you more of that in the next little section. So what I'm going to do here is I'm going to try to show you that entropy is a state variable for an ideal gas. So I'm going to try to prove that S is a state variable in an ideal gas. It's a state variable for anything. This applies not only to ideal gases, but I'm just going to do the proof for the ideal gas. Okay. Let me start with the first law of thermodynamics. dq is equal to du plus dw. Okay. So it's always good to start with the first law of thermodynamics. First, I'm going to remind you that heat is not a state variable. So let's first specify to a reversible process. So that will be du plus the work done in a reversible process. And the work done in a reversible process is PdV. Whoops. Okay. Now suppose I want to know the heat added in this, for example, this process which I showed up at the top. So let me just remind you that heat is not a state variable. And let me show you one way to see that. So let's say I go from some process. What is the heat added in some process from some initial state to some final state? Well, it's the integral starting at the initial state, ending at the final state of dq. And that's the integral initial to final du. Plus, let me break the integral into two pieces. Integral I to f p dv. Okay. Now this first integral, we know that for an ideal gas, we know that du is equal to CMV, sorry, it's equal to the number of moles times CMV times dt. Okay, so that first integral can be done pretty easily. So Q from I to F is equal to integral my number of moles, CMV, which is a constant, times dt. And since my integration variable is t, I'm going to integrate from ti to tf. Okay. Plus another integral which looks like this, p dv, from the integration variable here is v, so I'll go from vi to vf. Okay. The first integral I can do because the number of moles in CMV are constant, so I get nm CMV tf minus ti. But the second integral I can't do unless I know exactly how p depends on v, right? So this integral I can't do unless I know p as a function of v, right? because it's the area underneath the curve, and the area underneath the curve depends on the shape of that path. So you see the heat Q here is not a state variable because it depends on the path, right? Q depends on the path. So Q is not a state variable. Q, I to F, depends on the process, and so it's not a state variable. So what about entropy? For an ideal gas. Let's again start with the first law of thermodynamics. dq in a reversible process is equal to du, which is number of moles, CMV dt, plus PdV. So what did I do here? I did dq reversible is equal to du plus dw in a reversible process. So that's started with the first law of thermodynamics, and then I just substituted in for an ideal gas, du is number of moles CMV dt, and the work done is PdV. But now let me divide by the temperature everywhere. So divide by T, divide by T, divide by T. The left side is entropy, so ds. So ds is number of moles, CMV, dt divided by T, plus P over T times dV. And now let's see what happens if I integrate this. So delta S, the change in entropy, that's the integral from some initial state to some final state ds. And so I've got two integrals. The first integral looks like this: number of moles, CMV, dt divided by T. And the integration variable is T, so I go from Ti to Tf. And then I've got a second integral, P over T dV. And the integration variable here is V, so I go from Vi to Vs. All right, now the first integral is no problem. I can bring the number of moles, that's a constant. I can bring CMV out in front, that's a constant. And then I have this integral, Ti to Tf dt over T. And that is natural log of T evaluated at Ti and Tf. First integral, easy. Now the second one, it looks to start like it looks like I'm going to need to know the path again. But let me use the ideal gas equation of state. So ideal gas PV equals number of moles times R times T. So P over T is equal to number of moles times R divided by V. Okay. Let me substitute that in here. So what do I have here? Integral Vi to Vf. Number of moles, R dV over V. And the number of moles and the R can come outside the integral. And you notice I can do this integral, right? dV over V, that's easy. I didn't need to know the path. I didn't need to know the shape of the curve. Everything just works out. So let's see what we have here. Number of moles times R times the natural log of V evaluated at Vi and Vf. So what do I have here? Delta S. Let's pull out a number of moles here, Nm. And then we've got CMV times the natural log of Tf minus the natural log of Ti. And then I've got plus R times the natural log of Vf minus the natural log of Vi. And let me combine those logs together. CMV times natural log of Tf divided by Ti plus R times the natural log of Vf over Vi. This equation, which I just derived, shows you that the entropy change is independent of the path. All it depends on is the initial and the final points, right? That's a state variable behavior. So delta S in an ideal gas process, that's what we just derived. And you notice that it depends only on state variables. So that means that S is a state variable. Let me try to summarize. We started off by looking at the Carnot cycle and noticing that if I took the heat added divided by the temperature of the system when I added the heat, and I went around the whole cycle, I ended up with 0. It was a hint that there's a new state variable hiding there. We call this state variable entropy, dq divided by T, the heat added to the system divided by the temperature of the system when you add that heat. If you want to add up, find the finite change of entropy, you just add up all of the tiny changes. So I have to do this integral. And I showed you for an ideal gas that unlike the heat added in some process, which depends on the path because heat is not a state variable, the entropy change in this process only depends on the initial and the final point and doesn't depend on how I got from one point to the other. So we've got this concept of entropy now, this new state variable which was hiding, which had been escaping us for so long. Now where we have to go next is to figure out what does this have to do with the second law of thermodynamics. So that's the next topic. So we'll pick it up there, and I'll see you all in class. Bye for now.